Thank you very much. I'm very happy to be here. So thank you for the invitation to give this talk. So yeah, my title is Universally Counting Curves in Calabi-Yau Threefolds. Right. So there are many ways of enumerating curves in algebraic variety, in particular complex threefolds. So if you begin with just the space of smooth curves in your variety, this has canonical, what you might call, say, a derived intersection structure. So I think the way I like to think about this is structure of a derived scheme, which is tangent complex of degree 0 and 1. But there's more classical shadows of the structure, perfect obstruction theory, which is sufficient to define whatever enumeration you want to do. So how should you think about the structure? Well, it's the structure which exists intrinsically on a possibly non-transverse intersection of smooth subvarieties and ambient smooth varieties. So I have a smooth variety, two smooth subvarieties. The intersection might be a transverse intersection, in which case it's also a smooth subvariety. But if it's not, you can take of a derived fiber product, derived intersection, and that's some intrinsic structure this intersection carries, which remembers the intersection pairing of the original two cycles. Okay, so that's some structure, and the space of smooth curves. It's not obviously in any obvious way it's an intersection of this form, but it also carries the structure, and hence has this notion of counting with multiplicity. Okay, so if you want to enumerate curves, you need to integrate over a compact space, and space of smooth curves is usually not compact, even if we fix the homology class. So one way to obtain curve enumeration theories is to compactify the space of smooth curves in a way which carries a natural extension of this virtual fundamental cycle, this derived structure. If you didn't have to do that, you could choose any compactification. You can use the space of all holomorphic one cycles, say in that particular homology class. But as far as we know, the space of one cycles doesn't have any natural derived structure like this. All right. So now it's specialized to dimension 3. These are two examples of curve enumeration theories, which are most relevant to the talk. So let's say we have a projective threefold and fix a homology class. And for simplicity, let's assume it's term number 0. So there are two ways of viewing curves. You can view curves as the image of a map from some domain into your variety, or you can view your curve as being cut out by some equations. And the first perspective leads naturally to this notion of Gromov-Witten invariance. So I guess probably I should attribute it to, well, in the symplectic literature, it's definitely attributed to Gromov, but when you take smooth curves and add in maps from nodal curves, that you get a compact space. So of course, a smooth curve is viewed as a subvariety might degenerate to have some awful singularity, but if you want to view your curves as maps, then you don't need arbitrarily bad singularities. Nodes are enough. Okay, so then this is a compact space, and moreover, there's a natural notion of counting with multiplicity. It has this derived structure, virtual fundamental class, and you can write down these invariants. So on any compact space of cycles, say maybe fixing the homology class, this moduli space it's not compact because the genus can get arbitrarily large. The Euler characteristic can get arbitrarily negative. So that's why we need this formal power series, formal Laurent series expansion here. Oh, and the other way of enumerating, thinking about moduli space of curves is by regarding them as zero sets of equations. Another way of saying that is closed subschemes. So, the first thing you might try to write down is just all closed subschemes of dimension the most one. And it turns out, not a trivial fact, that when you're in dimension 3, this is compact. Well, it's always compact, but sorry, I should have specified the homology class here. If you specify the homology class and X is projective, then it's with projective, then it's compact. Yeah, so then it's a non-trivial result that in dimension 3, this space has a natural notion of counting with multiplicity. And so then again, you can define your curve enumeration invariance by integrating over the space. So the second definition, these invariants, this is sort of specific to dimension 3. Gromov-Witten invariants work in any dimension. So closed subschemes of dimension the most 1 can be curve components. They also have point components, and technically speaking, the point components cause some difficulties. You'd rather just have curves, and so later Ponder and Thomas came up with a more complicated moduli space. These gadgets are called staple pairs, and you'll notice now the support is somehow pure of dimension 1. So not only is the support of F dimension 1, but in fact every subsheaf of F has support of dimension 1. So there's no skyscraper sheaves at all. So it's a more complicated space, but it's actually easier to deal with at a technical level. So that's, and in fact, these are invariants which will play a bigger role here. Okay, so there's really no nice, even as far as I'm aware, there's no even conjectural geometric relation between these two compactifications of the spaces of curves. And these are just two ways of enumerating curves. There are many more. And nevertheless, most calculations show that these have been calculated in many examples. As far as anybody knows, they have the same enumerative content. They're all related by changes of variables. Okay, so first, Bridgeland proved that Ponder, Thomas, and Donaldson-Thomas invariants are well, the generated functions aren't equal, but they're related by this formula. So they have the same content. And this is not non-trivial result, but at least both sides sort of lie in the same world, in the world of sheaves, enumerating sheaves. It's a more difficult question to relate GW and PT. So this is conjecture of MNOP from 2006 says that you make this change of variables, Q equals e to the minus IU, and the power series are the same. Now it's interesting to note here that these are expansions around Q equals 0 and U equals 0, and yet if I substitute U equals 0 here, I get Q equals 1 and then the change of variables. So it's not a priori makes sense, this change of variables. You cannot input minus e to the IU into a formal Laurent series in Q. So you need the second part, which is that PT is a rational function of Q, in order to even make sense of the first statement. And moreover, since the change of variables is not doesn't respect the point which you're expanding around, this doesn't reduce to some infinite sequence of linear relations between GW and PT, as it would if you were expanding at the same point. So you really need the entire expansion of PT. Okay. So this is known in many cases. Local curve is just the total space of a rank 2 vector bundle over a curve. That's non-compact, but you can view it C star covariantly and get enumerative invariance that way. Okay, so the GW and PT are both computed for these. Same for toric varieties. And much later, Ponder, and Pixton proved this for complete intersections and products of projective spaces. So okay, more generally, what they showed is that if you have your variety has a sufficiently nice degeneration to a toric variety, then you can leverage the result for toric varieties to prove it for your variety that you degenerate to a toric variety. And I don't think there's known any example which you can prove does not have such a degeneration. So it's possible Punder, Punnett, Pixton actually proved it for everything, but we just don't know that it's everything. Okay, so the result I'll talk about today is that this correspondence holds whenever your variety is maybe I'll call this semi-Fano, so all anti-canonical classes is non-negative on all curves. And for the experts, we deal just with primary insertions, so pulling back cohomology classes from X. We don't do any descendant classes. Okay. Okay, so now I'll try to say something about the proof of this result. So first, I need to recall some algebraic topology. So if we have a map of spaces pi from W to B, you can take this sort of strange homology cohomology group of it, which is you can try to take homology of the base with cohomology of the fiber. Dually, you can try to take cohomology of the base with coefficients and homology of the fiber. And you might think that homology and cohomology due to being, multivariate and covariant, you just can't combine them in this way. But in fact, somewhat surprisingly, perhaps that you can. And okay, you can of course try to do the same thing for any homology or cohomology theory for algebraic varieties, of which there are many. But for me, I'm just going to use the singular homology theory. Yeah. So when the base is a manifold, then you can use Poincare duality to trade between homology and cohomology and just write this bivariant group as an ordinary homology or cohomology group. And the same thing when W is smooth over B. So it's a manifold bundle. Yeah, but in general, this is not reduced to any sort of homology or cohomology of a single space. And I'm really unsure what the correct notation for these groups is. And it's homology in one direction, cohomology in the other direction. I've sort of chosen arbitrarily that the notation reflects what you're doing in the fibers rather than what you're doing in the base. Now, the reason this is relevant is that this is where like a relative virtual fundamental class naturally lies. So by a single scheme with a perfect obstruction theory, virtual fundamental cycle lies at homology rho infinity. Now, suppose I have a family of spaces, and I have that's pi from W to B, and I have a relative perfect obstruction theory. So roughly speaking, that means the fibers carry virtual fundamental classes. So what does that mean? Well, on each fiber, I have a virtual fundamental class, and for a path in the base, I have, you might say, a bordism between this class and that class. And for every, I have a chain whose boundary is this one minus that one. And for every two simplex, I can look at those chains on the boundary, and I have something filling that in. So if you think about what homology group captures such things, you naturally will come up with this definition of this bivariant group. So cohomology of the base with coefficients in fiberized homology rho infinity of the fibers. Okay. So I'm not actually sure the right reference for the construction of this relative virtual fundamental class. Certainly not in starting on a singular homology setting. First, Barrett and Fantacchi defining an absolute case B as a point, and yeah, many authors defined it in these bivariant theories. Okay, so if there's one definition you should understand in this talk, it's this one, but it's a complicated one, so we'll spend some time on the slide. Right. So the idea of the proof of this this result is that we're going to find some sort of universal curve enumeration invariant, which takes values in some big uncomputable group, and we're going to compute that group actually, and compute that it's freely generated by local curves. And so the real result is not this the statement about MNOP that I said a few slides ago, but you take any curve enumeration theory for threefolds, then it's determined uniquely by what it does on the local curves. And there's an important caveat, which is it's not for all threefold, it's only for this semifinal. But the semifinal hypothesis doesn't come in until later. So for now, we just look at a universal curve enumeration invariant for all threefolds. Okay, so the first thing I need to define is this relative space of cycles. So if I have a family of complex manifolds, well, if let's forget about family, a single complex manifold X, then Z of X will be the space of one cycles. Now, I didn't write it on the slide, but it's very important. The complex manifolds I'm going to be considering, we need them all to be, we need to allow them to be non-compact. It's important for just fundamentally what the strategy is. The goal really is to show that if you have a complex threefold, then it's enumeratively equivalent to some linear combination of local curves. And those are non-compact. This deformation from an arbitrary threefold might be closed to a sum of local curves. It definitely passes through non-compact threefolds. So this family X to be, it's not proper, no assumptions at all. But the cycles are always compact. We only ever consider compact curves. So Z of X is the space of compact one cycles in this manifold X. One cycle is just a linear combination of formal non-negative integer linear combination of irreducible curves, compact irreducible curves. Okay, and when I write Z of X over B, that's just a relative construction. So it's a fibration over B. The fiber over a given point is the space of one cycles in that fiber. Okay, so given this space, you can given this construction, this is valid for any family. So in particular, I can take the universal family. So there's no well-behaved universal space of all complex threefolds, but I could pretend there is, and I can write down this space of universal space, the space of one cycles in that universal family, and take its relative, its bivariant group here. So that's homology of the base of coefficients compactly support cohomology of the fibers. And so that's not so well defined the way I said it, because CPX3 is some horrible complex analytic stack. But in fact, I don't want to consider all complex analytic spaces B. I want to just consider the simplices. And the reason is because, as I say, in this, to analyze this group, we're going to do a lot of cutting and pasting of families, and it's easy to cut and paste simplicial complexes. It's more difficult to cut and paste the complex analytic spaces. So in fact, I'm just going to consider this double complex right here. So let me try to explain what this actually means. So it's supposed to be the sort of universal space of insertions, the space of cohomology classes space of constraints you can put on curves, the space of curve enumeration configurations, which you could try to enumerate. And anything in this complex, you can pair with a curve enumeration theory, such as global fitting theory or theory, to get an actual number. So let's consider just the p = 0 part. So then that's just the direct sum for all complex threefolds of compactly supported cohomology on a space of cycles. If I have compactly supported cohomology class on a space of cycles, I can take any virtual fundamental class I got anywhere at all, push it forward to the space of cycles, and take the and integrate. Now that works because the cohomology class I had was compactly supported. That's what pairs with virtual fundamental cycle class, which is a Burrell-Bohr homology class. So I don't need this family X over B to be proper. I don't need X to be compact. Just take any compactly supported cohomology class in this space of cycles. Right. Now, if I were just saying, let's take the universal curve enumeration invariant of complex threefolds, then I wouldn't need any higher, in terms of higher values of p. Just p = 0 is enough. So what are these? What does p = 1 tell me? P = 1 is encoding the fact that I want curve enumeration theories which are deformation invariant. So I have a family of threefolds, and over the interval, then the Gromov invariance of pi = 0 equals the Gromov invariance of pi = 1. And you can encode this by looking at this relative space of cycles for this family over the interval, and saying that for any cohomology class in my relative cycle space, I integrate it over 0 or I integrate it over 1, and I get the same. And the higher values of p are giving you higher family invariance over all arbitrary bases. Well, not quite arbitrary bases, just base being simplicial complexes. Okay, now you could do the dual thing, where instead of where I take cohomology of the base with coefficients and homology rel infinity of the fibers, and that's where the curve enumeration theories lie. So Gromov invariance or Ponder-Pan and Thomas invariance give you classes here. Okay, so this slide is elementary, and maybe, but it's intended to help understand the definition on the previous slide. So these are all examples of universal construction. The Brody group of vector bundles, this classifies Euler characteristics. So they have an Euler characteristic on vector bundles that is an assignment to each vector bundle as an element of some group, which is additive, and the assignment is additive under exact sequences. Then that's equivalent to giving a homomorphism out of the Brody group K0 of vector bundles. And if I calculate this group, then I've classified all possible Euler characteristics. And you can do this in many other settings. This scissors congruence is one which people like to study right now. You can take the abelian group on polygons in R2 and plot out by translation, rotation, and cutting your polygon to multiple polygons. And then the homomorphism out of this group is a sort of an exotic notion of area. But you can compute the group. And in fact, it's just equal to R taking the volume as an isomorphism. So there are no exotic notions of area for polygons in R2. For polyhedra in R3, there is an exotic notion of volume. It's called the Dane invariant. And in fact, that completely classifies all exotic notions of volume. So, and this group of scissors congruence in hyperbolic free space, I think, is not known. So in higher dimensions, these get very hard to compute. Okay, so the idea, just going back, the idea of this group is exactly the same. So this is the group in which the universal curve enumeration invariant is valued. And if we can compute this group, then we've classified all curve enumeration invariants. Okay, so this is now state sort of this result, which I alluded to earlier. So we only look at the semifinal cycles. So those are the cycles where all of the components have non-negative Chern number. That's an open subset. So I can make the same definition from 2 slides ago, where I just look at the semifinal cycles, form a Groton D group out of those. That's this group here with rational coefficients. So the result is that this this group is the free polynomial algebra on these local curve elements. So in the Calabi-Yau setting, k equals 0, you take curves with arbitrary multiplicity. In the Fano setting, when k is positive, you just have a local curve of multiplicity 1. Once you give higher multiplicity, those are 0. Okay, so there's this recent paper of Ionel Parker, which is an inspiration for all this. And what they proved is they proved the Gopa-Kromov integral object. So linear combinations of Gromov invariants are integers. And the way they proved this was they proved something actually much better, which is that they proved any curve, any symplectic sixfold is enumeratively equivalent to some linear combination of local curves. And the way they did this was with generic transversality. Almost complex structures are very flexible. You can perturb them, and when you do that, your curves generically are isolated. It's a little bit more complicated than that. An isolated curve could have multiple covers which sort of converge to it. But that's the basic idea. You do some perturbation to achieve transversality, make everything isolated. So we're just going to try to mimic that argument, but there's an immediate problem, which is that complex structures don't have any local perturbations. A closed complex manifold, it may have no deformation of the complex structure at all. So, but nevertheless, there's a weaker version which is true, and to leverage that to prove this result. Okay, so what does generic transversality say in almost complex geometry? So I have a target manifold, and I take a generic almost complex structure. So an almost complex structure just means I make the tangent bundle a complex vector bundle. And when X is a Riemann, when X is two-dimensional, two real dimensional, then all of these are integrable. All of these come from Alice's complex analytic charts. But in higher dimensions, this is no longer the case. And these are very flexible. You can make compactly support perturbations to these. And if you choose J generically, it's perhaps not so surprising that all the holomorphic maps from curves are unobstructed. So this is not a hard result, but technically very useful. So what are we gonna do for complex structures? Well, we have to give up on the idea of perturbing the complex structure everywhere, because this might not exist. But if we already know if we have a curve already, and we're just interested in sort of perturbing that particular curve, or maybe perturbing alpha space curves near that particular point represented by this curve, then most of the threefold is entirely irrelevant. You just throw it away and just restrict to a neighborhood of that curve. And the neighborhood of this curve now will have a very, very large set of perturbations of the complex structure. And this leads to a problem which seems a little bit circular. So I perturb the complex structure as a function of which curve I'm enumerating. And so now the new moduli problem we're trying to consider now sort of says I want curves which are holomorphic with respect to a complex structure which depends on that curve, which seems a little bit circular, but it can. What we need to do is make sense of that. Okay, so this statement is hopelessly vague, but I tried to give you some short summary of what goes on. We'll get to more precise statements later. So generic map dependent local complex structures achieve transversality. Achieve transversality means everything is unobstructed. Okay, so these are the sort of deformations we're going to consider. So if I have a complex manifold and divisor, I can view it as the gluing of the complement of the divisor and a neighborhood of the divisor. That's a two-element open cover. They overlap over the function neighborhood of the divisor. And I can try to reglue so that the complex manifold is glued out of two pieces. I can change how I glue. The way I might change how I glue it, at least up to first order, would be by choosing a vector field over that intersection. The intersection is sort of the punctured neighborhood of D. So if I have a section of Tx over that punctured neighborhood, then I can use that to reglue, or I can use the flow of V to reglue. Call this a divisorial deformation. So one way of thinking about this, right, is at least up to first order, right? Deformations of X is supposed to be H1 of X with coefficients in the tangent bundle of X. And this is a check one cocycle for this particular covering. Okay, so that's the sort of deformations. I've tried to illustrate that here. The green is the divisor. It's important to keep track of the difference between the divisor and the curve. So the divisor here is green and the curve is red. Oh, so if you want to make a cycle unobstructed using these sort of deformations, you better intersect all the irreducible components of the curve. So that's what this notion of being D-controlled means. If your curve has a component which is entirely disjoint from D, you're not going to be able to use D perturbations to make it unobstructed. So this is sort of minimum cost you need the definition unobstructed. Okay, and the not hard lemma is to show in fact it's sufficient. So if you have is not so significant. So in practice, we have a curve, and remember we've restricted to a very small neighborhood curve. So the divisors are just sort of transverse disks at various points along the curve. So those are affine in the relevant sense. You just need to have enough sections of this space. Okay. So I've sort of already talked about this moral here. You can perturb your complex structure, perturb your target to make everything unobstructed locally near a particular one cycle that you might try to enumerate. Okay. So now we'll see in a couple of slides, there's this thing which Pandit calls the graph trick, which is you used to re-express a given curve enumeration theory as a family enumeration theory, in which at every point of the base, you only care about one cycle. You're just enumerating curves in nearby one cycle, and then you can do this local perturbation is enough. Okay. Yeah, so this is a sort of technical step, but I think there's an interesting induction argument, so I think I should explain it. So remember this picture on the previous slide. You have a curve, and you choose your divisors. It's very easy. We just have a single curve, red curve, to choose divisors for the transverse control. There's nothing to do. Just write them down locally. But eventually we need to deal with families, family enumeration problem, where now we have a family of threefolds. There's some base B, X over B, and there's some family of cycles. So for each point in the base, I just have one cycle that I care about. But that cycle is sort of varying as I go around the base. And I need a divisor which also varies and controls the cycle as I move it around the base. And suddenly this creates what you might regard as a problem, which is that if you just naively try to pick divisors, then they may intersect each other. So if B is just a point, a single threefold, I choose divisors, it's easy to make them disjoint. But if now you have a one-parameter family of threefolds, a one-parameter family of cycles, you need a one-parameter family of divisors. Well, they move around, and okay, the one-parameter family of divisors won't intersect. But once you get up to a two-parameter family, they will start intersecting each other. So this proposition, which I'm just calling enough divisors, says that you can get out of this predicament. You actually can choose divisors varying in the base parameter, which control all the curves and all the cycles you care about. Yeah. So X to B is my family of threefolds, which we care about. We form the relative space of cycles. K is this space of cycles we want to control. So K mapping to B being injective, that's saying for every point of the base, there's at most one cycle we care about. Okay, now we're going to trim X, which is this procedure I already mentioned, right? We throw away everything other than a small neighborhood of the red curve we care about. And after doing that, we can find divisors, relative divisors. So yeah, the proof is an induction. So if you choose to divide them generically, they're going to be disjoint, except for a codimension 2 subset of the base. And now, but over that codimension 2 subset of the base, I can assume that the result is true by some induction hypothesis. Induction on the dimension of the base. So anyway, I found this argument interesting. I hadn't seen this sort of induction combined with general position before. Usually I think of general position as the best you can do. General position tells you something fails on some codimension, and it will actually fail on that codimension. You can't do that. But in this case, apparently you can. Okay. So now I want to form a Grothendieck group of the transverse cycles. So now we're dressing up all of this generic transversality geometry into the algebra to get back to make contact with the Grothendieck group that we eventually want to calculate. So the idea is we define a Grothendieck group using only the transverse, the unobstructed cycles, and then we compute that, and then we show they're the same by generic transversality. So it's not exactly clear what it means for a cycle to be unobstructed, right? This way, again, by saying that the space of cycles doesn't have a perfect obstruction theory. It doesn't have this natural derived structure. So I just make the sort of dumb definition that a cycle is regular, we'll call it semi-regular, when I just take the normalization of all the components. That's a map, and I ask for that to be regular in this very strong sense up here. So I call a map regular when its deformation theory is unobstructed, even when you impose all the possible constraints that satisfy. So two points being mapped to the same point, or the derivative vanishing at some point. So this implies that in particular the curve itself with no constraints is also unobstructed. It also means that all these constraints sort of you can deform the curve so they don't occur. So if a map is regular, then you can always deform it transversely to make it a smooth embedding. Okay, so I say a cycle is regular when this map of the normalizations of all the components is regular. Now, deforming just the map from those normalizations of the components doesn't give you many deformations of the cycle. The cycle can deform in many other ways. The components can merge. You can have a component with big multiplicity splitting into many components of single multiplicity. So this notion of semi-regularity does not tell you how, does not say anything about those. It does not take those into account. So it's a working definition which works for this result. I'm not saying it's a great notion on its own. Okay, so you can restrict the interior of this locus. Usually, the locus is the locus where something is unobstructed is usually open, but this is, well, it is open, but with semi-regularity is not unobstructed in this condition. So it's not open necessarily. We can have to take the interior. So use the interior, we can define this homology group again. Semi-regularity, interior semi-regularity does not play well with restricting to strata. If I have a family over a simplex, then and I restrict it to say one of the sides, vertices, then I can have a point which is the interior of the semi-regular locus over that vertex, but maybe it's a limit of non-semi-regular things over the interior. So there's no real total space here. It's not a bivariant group, but I can still write down the complex. Okay. Yes. Okay. So now these are I think these are the theorems I stated in words just now. So right now we need to restrict the semifinal. So if we restrict to the semifinal, then the interior semi-regular group. So this universal curve enumeration invariant of unobstructed curves. Well, that's an elementary dimension count just says this is freely generated by Poincare duals of smooth points, what you might call geometric local curves. Everything is transverse, so it's just a dimension count. Now, the real non-trivial result is the fact that restricting to the interior semi-regular curves doesn't change anything. So it's the same. You get the same Grothendieck group, and the statement is that, and what it's saying is that any configuration of curves you might try to enumerate can be perturbed and shown to be equivalent to some enumeration problem involving only unobstructed curves. Oh, and the proof of this is we use this generic transversality result of the previous slides. First we take our insertion, we expand the base in order to make it supported over some space of curves mapping injectively to the base, and then we can apply divisors and generic transversal. Okay, now there are a few loose ends to tie up to get the main result. So first, we need to compare the geometric local curve elements and the equivariant local curve elements. So geometric local curve elements was just literally I have an unobstructed curve. I want to count enumerate that with the Poincare dual at that point in the moduli space. Equivariant local curve element says I have a curve, a rank 2 vector bundle, and do C star equivariant invariance. So I don't know whether these are the same. In fact, I don't even know whether the geometric curve local curve elements depends only on its sort of topological type. It's interesting to note in the real setting, in an almost complex setting, Ian and Parker showed that the geometric local curve elements do not depend only on the topological type. There's some wall crossing. If you have a unobstructed curve, another unobstructed curve of the same GNC Chern number, and you form the almost complex structure from one to the other, generically you pass through some walls where multiple covers fly off, and they're not equivalent. But they are equivalent modulo things of smaller covering multiplicity. And that's what we can show here. So geometric and equivariant local curve elements are the same modulo things of smaller covering multiplicity. So by an upward triangular argument, they generate the same thing. Now, you might expect that since we're in a sort of complex setting, integrable complex setting, that there's no wall crossing. And any sort of condition which might create a wall crossing will be complex codimension one. You can avoid it. I don't know how to make that precise. Okay, the other loose end is that okay, so far what I've described shows that these local curve elements, they generate the Grothendieck group. So everything is every complex threefold is enumeratively equal to the sum combination of these. Now, I think if you think really hard about this argument, probably you can extract free generation out of it. But in fact, you don't need to. This group has a lot of algebraic structure. It's a bialgebra, and it also has endomorphisms which sort of divide the multiplicity by some any non-negative integer. And using those operations, you can take any element in the kernel of this map and sort of iteratively simplify it, iteratively reduce it until you get something which you can show has non-trivial Gromov-Witten invariant, hence actually can't be in the kernel. So in fact, if it's surjective, then it's also, well, I think maybe I don't need to say if it's surjective. It's just it simply is always injective. So there's this Milner-Moore theorem on the structure of graded bialgebras, which is a very similar statement. I don't exactly see how this is a special case of that, but the proof is certainly very similar.